Have you ever wondered how scientists determine the concentration of a particular element in a sample? Well, let's unravel the mystery together. They use a technique known as Atomic Absorption Spectroscopy, or AAS for short. This is not just any ordinary process, it's an analytical process that can accurately and precisely determine the concentration of elements. Think of it as a detective, sifting through the clues to find that one unique element in a sample. From environmental monitoring to archaeology, AAS plays a crucial role. But today, let's focus on its role in the pharmaceutical industry. Here, AAS is used to check the purity of drugs to ensure what we consume is safe. It's like an unsung hero, working behind the scenes to ensure the quality of our medicines. And to understand how this fascinating process works, we need to dive deeper into its theory and instrumentation. So buckle up as we embark on this scientific journey. So what's the underlying theory behind atomic absorption spectroscopy? Glad you asked. In its essence, atomic absorption spectroscopy, or AAS, is a technique used to identify and measure the concentration of specific elements within a sample. It's like a detective tool for atoms, if you will. At the heart of AAS lies the principle that atoms absorb light at specific wavelengths. Picture a sea of free metallic ions, each with a unique signature wavelength of light they prefer to absorb. This is where the magic happens. These ions, when exposed to light of their signature wavelength, absorb it, causing them to transition from a ground state to an excited state. Now, this might sound like a fun light show at a microscopic level, and it is, but there's more to it. The amount of light absorbed is not random. In fact, it's directly proportional to the concentration of the element in the sample. This means that the more of a specific element you have in your sample, the more light it will absorb, and vice versa. This relationship is governed by the Beer-Lambert law, a cornerstone of spectroscopy. It states that the absorbance of light by a substance is directly proportional to its concentration, provided the path length and wavelength of light remain constant. So, in a nutshell, AAS is like a concert where metallic ions are the audience, and light of different wavelengths is the music. Each ion has a favorite song, and the more they like it, the louder they sing by absorbing more light. And by measuring how much light is absorbed, we can figure out how many of these fans are present in our sample. AAS is not just a fascinating theory, but a practical tool used in various fields, from environmental studies to forensic science and, of course, pharmaceuticals. But we'll get into that later. Now that we've grasped the theory, let's explore the instruments that make this process possible. The operation of atomic absorption spectroscopy relies on a set of specific instruments. Let's delve into the essential components that facilitate this fascinating process. First up, we have the light source. This is the initial stage of the procedure, where a hollow cathode lamp or electrodeless discharge lamp generates light. This light contains the specific wavelengths that correspond to the atomic absorption lines of the elements to be measured. It's like shining a flashlight into a dark room to illuminate what's inside. Next, the light from the source is directed towards the atomizer. The atomizer is where the magic happens. It's a chamber where the sample is introduced and atomized. There are two types of atomizers, flame and electrothermal. The flame atomizer is used for the analysis of major and minor elements, while the electrothermal atomizer is used for trace element analysis. The atomizer is like a stage where the elements strut their stuff. The light then passes through the monochromator, our third key component. The monochromator is essentially a filter. It isolates the specific wavelength of light that will be absorbed by the atoms in the sample. It's like picking out a single voice from a chorus, ensuring that we're only listening to the part of the spectrum we're interested in. Finally, the light arrives at the detector. The detector measures the amount of light that reaches it after passing through the sample. It is this measurement that gives us the concentration of the element in the sample. It's like the judge in a singing competition, assessing the performance and giving a score. Together, these components, the light source, atomizer, monochromator, and detector, form the backbone of atomic absorption spectroscopy. Each plays a crucial role, and in harmony, they enable us to measure the atomic absorption, which provides invaluable information about the sample being analyzed. With these instruments, we can measure the atomic absorption, but there's more to it. Let's discuss line broadening, and the Doppler effect next. What are line broadening and the Doppler effect? And how do they impact atomic absorption spectroscopy? Well, let's start with line broadening. In an ideal world, the absorption of light by an atom would happen at a precise frequency, resulting in a sharp line on the absorption spectrum. But we don't live in an ideal world. Instead, we encounter line broadening, where these absorption lines are broader than expected. This broadening arises from two main causes. The first is natural line broadening, which is a quantum mechanical effect. Without getting too deep into quantum mechanics, let's just say that the Heisenberg uncertainty principle plays a role here. It tells us that we can't simultaneously know an atom's energy and the time of its transition with absolute precision. This uncertainty leads to a natural broadening of the absorption line. The second cause is pressure broadening, which occurs due to the interactions between atoms. As the gas pressure increases, atoms collide more frequently, which interrupts their absorption of light and broadens the absorption line. Now let's move on to the Doppler effect. We've all experienced the Doppler effect when an ambulance passes by with its siren changing pitch. In the context of atomic absorption spectroscopy, the Doppler effect causes a shift in the frequency of light absorbed by atoms moving towards or away from the light source. This motion results in a broadening and shift of the absorption line, affecting the accuracy of our measurements. So why do we care about line broadening and the Doppler effect in atomic absorption spectroscopy? Well, understanding these effects allows us to make corrections to our measurements, ensuring we get accurate results. Without taking these into account, we might misinterpret our data, which is something we definitely want to avoid when, for example, determining the concentration of a drug in a pharmaceutical product. Understanding these effects helps us to interpret the results of AAS accurately. Now let's move on to flame types. Different types of flames are used in atomic absorption spectroscopy, but why, you may ask? Well, it's all about creating the right environment for atoms to absorb light. First, let's talk about the air acetylene flame. It's the most common type of flame used in atomic absorption spectroscopy, or AAS for short. This flame can reach temperatures up to 2,300 degrees Celsius, providing a suitable environment for most atoms to absorb light. Next, we have the nitrous oxide acetylene flame. This flame is even hotter, reaching temperatures up to 3,000 degrees Celsius. It's used when elements like aluminum, titanium, or vanadium need to be analyzed because these elements require a higher temperature to absorb light effectively. But it's not just about the flames. Interference is a significant factor in AAS. So what's interference? It's anything that alters the absorption of light by atoms and can lead to inaccurate results. There are different types of interference, including chemical interference, which occurs when an atom forms a compound and cannot absorb light properly. Spectral interference happens when the absorption lines of different elements overlap. And then we have physical interference, which could be due to changes in the flame's temperature or composition. But don't worry, there are ways to correct these interferences. For chemical interference, we can add releasing agents that break down the compound and free the atoms. For spectral interference, we can adjust the wavelength of the light source to avoid overlap. And for physical interference, we can control the flame's temperature and composition to ensure a consistent environment for atoms. So there you have it. The different types of flames and interferences in atomic absorption spectroscopy. It's a delicate dance of heat, light, and atoms, all working together to provide accurate and reliable results. Armed with this knowledge, we can now look at how atomic absorption spectroscopy is used in the pharmaceutical industry. Scene script. Atomic absorption spectroscopy has a significant role in the pharmaceutical industry, but how exactly is it applied? Let's start with quality control. Atomic absorption spectroscopy, or AAS, is used in the pharmaceutical industry to scrutinize and ensure the purity of drugs. The process involves determining trace elements in pharmaceuticals, for instance, checking for any unwanted metals in the composition. Next, AAS plays a crucial role in the research and development of new drugs. It assists in the analysis of biological samples, as it can accurately quantify the concentrations of various elements. This helps in understanding the effect of a drug on the body's metabolism and its potential interactions with other elements in the system. Finally, AAS is also used in environmental monitoring within pharmaceutical facilities. This ensures that the manufacturing process doesn't release harmful substances into the environment. So there you have it, a deep dive into the world of atomic absorption spectroscopy. Subscribe for more because you won't find me later.